Good afternoon, everyone. We are happy to give a talk about the Android bundle, the bridge to root. First, we would like to introduce ourselves. This is my colleague, Hongli.
Hello. I'm Hongli Han. I'm a security researcher at the core team of Qihu 360, and I mainly focus on the AOSP and kernel bug hunting and exploitation.
I am Mingjian. I'm the leader of core team. So, what does the core team do? It's a security-focused group started in the middle of 2015. We focus on the Android and Linux platform security research and aim to discover zero-day vulnerabilities, develop POC, and exploit. We have found more than 200 CVE. In 2017, since we submitted so many high-quality reports to Google, Android VRP rated our team as an Android top research team. This slide, I would like to introduce what bundle is and why bundle. Bundle is an Android-specific IPC mechanism. It's implemented as a driver in the kernel. Here is a simple architecture of bundle IPC. It's used for nearly everything that happens across processes in the core platform. What's more, bundle was accepted in the main Linux kernel in February of 2015. Bundle is so important that it's one of the most attractive attack surface on Android. We have done some work around the bundle driver. For example, we analyzed the possible attack surface by code auditing and fuzzing. We are lucky and found some bugs, like CVE 2025 and other zero-day vulnerabilities. Furthermore, we explored them to gain the systems and root privilege. Especially the CVE 2025. With this single vulnerability, we root the latest Pixel 3 XL. As far as we know, it's the first time the Pixel 3 XL has been rooted. Next, I would like to introduce the root cause of CVE 2025. First, I would like to talk about some basic background knowledge about the bundle IPC. Simply, there are 4 steps during the bundle IPC. Step 1, the client sends the BC transaction to the driver. Step 2, the server reads the BR transaction from the driver. Step 3, the server sends the BC reply to the driver. Step 4, the client reads the BR reply from the driver. The client, the driver, and the server share the same physical memory. The client maps the memory to its own address space and accesses it with a user point. The driver accesses the memory with a kernel pointer. There is a mapping between the kernel pointer and the user pointer. The driver uses the struct bundle buffer to describe the buffer used for transaction. When the server sends BC reply to the driver, what happened in the bundle driver? The driver allocates a band buffer object and then copies the reply data to the buffer data. When the client sends the BC free buffer and the user pointer to the driver, what happened in the driver? The driver maps the user pointer to the kernel pointer, finds out the band buffer object related with the kernel pointer, and then free the buffer and the band buffer object. So there is a question. What happens if client tries to free the reply buffer while server is doing BC reply? Is there any protection? Unfortunately, the answer is no. There is no lock to protect the band buffer object. After the object is allocated, there is a risk window. We can free the band buffer object before it's used. This would lead to a UAF problem. This UAF bug is an all-round vulnerability, because we can do the arbitrary write when server calling copy from user, because tbuffer is controlled. And also, we can do the arbitrary read when client calling copy to user, because tbuffer and tbuffer target are controlled. What's more, leaking kernel symbol is very easy. tbuffer data size, offset size, and data are all leaked. Band is so powerful, and so is a vulnerability. With this vulnerability, we can do arbitrary read, write, universal root, especially sandbox escaping. It affects Android devices in recent 2 years. So we gave the vulnerability a name, water drop. Water drop comes from the fiction, the three-body problem. The water drop destroyed nearly all of the Earth's starships, just like the vulnerability destroyed nearly all of Android devices. Next, my colleague Hongli would demonstrate how to exploit this bug.
Okay. This vulnerability is able to read or write anywhere in the kernel memory space. When trying to root the device, there are still several problems. First, it's really hard to produce this problem indeed, because the time window for triggering the malicious buffer free operation is very narrow. And second, it needs an efficient heap string function, so we are able to occupy the unexpected free buffer. Sorry. Okay. As mentioned above, in order to trigger the use of free problem, we should try to successfully execute the BC free buffer in such a narrow window. After the bundle a log new buffer is done, and before the code in line 3175 is reached, a symbolic coders between this time window is shown on the right side. It's really hard to run thousands of lines or assemble coders in such a narrow window. because it will check the user allow user free. If it's true, it will return. So the BC free buffer failed. And even it bypass this check, it will call the bundle alloc free buffer later. Them all checks here. They are all bug ons and system crash and reboot. So how to extend the time window? This is a good question. We try lots of methods, such as we study on the CPU frequency. In fact, the frequency on the PL3 is not the same. There are high one and the low one. So we try to allocate the low frequency CPU while freeing in high one. It seems that it goes further, but not enough. Then we study on scheduler, and we notice that the musex log it may affect the scheduler. Indeed, it is. It will call the wake up queue when the unlock event happens. What's more, when doing BC free buffer is called the mutex log. So we can let the freeing process waiting to be wakened by the server process thread and the client process thread into the CPU by keeping all the other CPUs busy enough. Also could call the scheduler set affinity for insurance. This works very well, a nearly 100% success rate. It's not easy to trigger this bug indeed because it needs the cooperation between the client process and the server process. In this section, I will detail how to trigger the vulnerability stably. In order to achieve this, we should think out how does the allocating and the freeing job works first, as shown between line 378 and 392. It will traverse the red-black tree to find the best fit one from the free buffers firstly. Then, if the buffer size of the best fit one is not equal to the wanted size, it will call kzalloc to apply for a new one. This one will be added to a free buffer red-black tree and will be used next time when applying for such a size bundle buffer object. Then, how does the freeing job works? As shown in 609624, it will check if the buffer is the last one. If not, the next one will be picked out and check the next free is true or not. And key free is called in bundle delete free buffer actually. Later, it will check if there is a previous one before the buffer. If true, it will free the base buffer and keep the previous one. In conclusion, the bundle job loves to keep the bundle buffer object with smaller buffer data value. So, how to trigger this vulnerability stably? I think we have the answer. We divide this into two parts. Step 1. Continuously request the server process to produce lots of the reply and should avoid calling the destructor of the parcel because the destructor of the parcel will send BC free buffer to the kernel. It's out of our control. Step 2 is go like this. We should free this in reverse order. We create 2 threads. The thread 1 for sending BC free buffer, and the thread 2 for sending BC transaction, as shown in the finger. We free the buffer in reverse order, and the kernel will unlock or free by the ruler mentioned above. When the BC free buffer command from the client process and the BC reply command from the server process happen at the same time, the OF problem could be triggered. This is a long window for doing heap spring too. By such a process, we can trigger this vulnerability very stably. In this session, we will detail how to leak the kernel symbols with this vulnerability. As you see, the date side, the offside we have mentioned above is the leak points. We use the mutex lock mechanism to extend the time window and spray after sending BC free buffer to the kernel. So when the server process is waked up again, it will set the target node to null pointer and to pointer in 3178 line. So it's not a good idea to leak the kernel symbol by the target node. But the date size, the offset size are available. And what about the data? The data will be treated as a writable address. When calling confirm to user, the data will be written to it. So if we want to leak info kernel symbols from the kernel, we should to satisfy these 2 conditions. First one of them could leak the kernel symbol, kernel info, and also the data should be the writable address, and no crash after being written. This makes it more difficult. Now, so if there is a method to bypass the checks of the T-buffer data in copy from user, this is definition of the copy from user. It's mainly do the check object size and the child function arch copy from user. It's happy to see the annotations skip all tests if the size is 0. So go on, let's check the arch copy from user. The arch copy from user returns bytes not copied. So the copy from user will return 0. If we make the tr date size 0, it will not go to the error branch. But if we set the tr date size 0, could we obtain a valid band buffer object and more? Let's check the code. The annotations pad 0 size buffers so they can get assigned unique address. That's great. We are still able to obtain a valid band buffer object. Now, we should think out how to make the tr date size 0. It's very easy, in fact. Find the Bander native service interface like this. It returns directly as no date routing to the reply. Now, we do not need to care about data anymore. Just try to leak the kernel symbol by the D size of size. So, how to find a valid info leak structure from the vast amount of coders work hard for 24 hours every day? No. You may try to solve the computer problems in computer way. We wrote a filter in the key-malloc and key-free. Then we make use of the fuzz tools to trigger all kinds of system calls. Then have a rest, wait for hours or maybe days, analyze logs and select one. Heap string skills are one of the most important parts when trying to exploit with a user-free vulnerability. The heap string skills used for exploiting the wardrobe vulnerability will be introduced in this section. Think about this. It's very time-consuming to find an available heap string structure. It should require no permission and bypass checks. Most of all, it could leak what we want. By hard working, we found it, but sadly, if the life cycle of it is out of control, it may cause many problems. Could we find an efficient method to turn the life cycle of it from uncontrollable into controllable? Think about the key-malloc and the key-alloc. The key-alloc is based on the key-malloc, but it will set the memory to 0 immediately after the memory is allocated, but the key-malloc will not. We take the object A and the object B. For example, the object A is released. Later, its memory is occupied by the object B, and is applied for memory by calling key-malloc. If the object B needs less than the given by the kernel, that will be even better. And if the life cycle of the object B can be controlled, the previous state of object A will be leaked, and the residual data will be kept. It works like this. First time, the unexpected release object released, and we occupied it and put the wanted date there. The next time, we occupied it to control its life cycle. This will be helpful when exploiting with a user-free vulnerability. We can use this to protect the unexpected free buffer caused by triggering this vulnerability. We are able to release it at a more appropriate time. Here, I will show an example about this. We will call the fsetchar tree to put the wanted data there, and then use the struct unnotified event info to gather life cycle. And we use the fsetchar tree instead of the setchar tree because it's more lightweight, and will not allocate an other size 128 slab object. It can help us write the wanted data to the unexpected release buffer when calling copy from user. The value here is the date we passed in. And the size of the struct unnotified event info can be set to a relatively small value. small value maybe a little bigger than 48. And it apply memory by calling keymalloc. So it could be used to guard the life cycle. You can use the FCHR tree to do guard spree too, or adjust the size to guard all spree more fast. It's one I show an example. If we say the user data now, it could be used for guard heap spree. The coder and the flag in strength. This one I would like to show a bullet spree for this vulnerability. We find the heap string structure around the band driver context. The coder and the flags showing on the left side has the same offset with the date in strength band buffer. They are all 88. So we can write BC transaction after BC free buffer in M out, and it will do heap spree immediately after BC free buffer finished. And we also use a mirror spree because the size 128 slab objects are frequently used. For example, within called spree functions, it will allocate another two size 128 slab objects before the target slab object is allocated. So how to deal with this situation? And we need to free another two symmetrically. This was well in our test. We have just talked about how to spree. It's time to use this vulnerability to do arbitrary write. As mentioned above, the reply date is obtained from server process, but sadly, we cannot create a server on nrow. We have an idea. Could we set the value to the server and get it back? After searching, we found two. The first one could help us control 2 bytes. It means we can arbitrarily write whatever data 2 bytes data. The second one could control 16 bytes every time. That's enough for our exploitation, and we will use this interface later to exploit the pixels. We do arbitrary write, but how do you know if it's time to stop? How do you know we have write success? We put a flag here, when spring, and check each time when we receive the reply. If we received the flag we have put, is success returned. And we have arbitrary ability now. Let's try to do arbitrary read. As mentioned above, we use the target node for arbitrary read, but it will be set to null pointer when the process is vacant. So we try to get heap spree method and call the fchar tree with size 88 and loops. We should also need to adjust the CPUs and control the spree time. Okay. Now we are able to arbitrarily write, arbitrarily read, and leak the kernel symbols. We'll try to root the devices. In the following session, I will introduce how to root the pixel device in two methods. The first one, create the crate directly. The second one, using the KSMA attack. So, how to leak the crate address with this vulnerability? It's not easy to leak the crate directly, and even we can arbitrarily read, but who knows where to read? We try to leak the base address, address of an object whose life cycle is controllable. Then we try to release it and occupy it immediately with the target object. Later, we could get a target value by arbitrary read. Here, I will introduce an easy-to-use heap string structure and continuing the crate. The F crate is also the credential of the process who is opening the file. It will call when opening a device or file, it will call the getEmpty flip. And in the 262, the F crate will be set to the crate or credential of the process. The single PT list could be leaked to us by using this vulnerability because the offset shown on the right side is 64. And the sync PT list point to a structure sequence object whose size is 160. It's also freed when the structure sync PT object is released. Then we occupied with the struct file object. Because it's 160 and the struct file is 256. So they will use the same size. Then we check the arbitrary read to obtain the credential address and write them to 0 to root directly. This is an example by attacking the F crate to root directly. And in this session, I will introduce how to root by the KSMA attack. This method is provided by Yongwang last year. It attacks the swapper PGDR to obtain the privilege to write the kernel coders. And it still works on Android device currently. But it needs to attack the Trump PGDR on Pixel 3 because the configure mapped kernel 80EL0 has been set in the Pixel 3 to defend the meltdown. It will unmap the kernel when running in user space. So we route it by the following steps: disable the SE Linux enforcing, set URD, JRD, URD, and so on to 0. And we set the correct secure bits to 0. This one is for by writing this one to 0, we are able to access the private directories of the apps. We write the coders of the get rest JRD and change the machine code to the right side one to write the URD, JRD, URD to 0. And call this one to write them to write the security bits to 0. And we should set the correct cap B set to 3F and 8F. And we route it. Okay, now I will show you a video. Oh, I'm sorry. It could not display here. How to?哦，它是切换成2个屏幕了。哦。Oh. This in the image version at the December 2018. This one bypass the key ASL. Okay. With this one. 这页点开这个 delete this. Okay, I'm back. So, this conclusion section. It's more and more difficult now to find universal root buggers on Android devices, but no system is safe. And we should find the gaps when digging bugs, because the smart files do very well now. We should find out what they cannot do. And difference make a difference. We should try new method and new techniques. Thank you, and so on. Any questions? Yes, please.
Thank you for your great talk and the technique here. Okay, thank you. So may I know that in your guard spray process, right, you are trying to find some controllable object that you can control the life cycle and the size. So you say that you try to find such object via some fuzzing technique. Is that right?
翻译一下。
说到了，就是你要寻求一个可控制的可控
就他最后
方式来控制这个生命周期，然后最后是他的意思是说，你们是不是说用一个 fuzzing 的方法找到了这样的一个对象
？Yes, we added a filter in key free and key malloc, and we run the fuzzer, so it could produce a lot of logs, and we are able to select one there.
May I know that how many of such objects did you find?
2. Because we found in not a long time, and we found a available one. We stop this.
Oh, okay. Okay, thank you.
Any more question?
Then I'd like to ask you to give a big hand to our speakers.